Hello students, let us now look into another biasing circuit which is called as 4 resistor bias network. Okay, so this 4 resistor bias network is also considered to be voltage divider bias circuit. We also call this as voltage divider bias circuit. Okay, voltage divider bias, which is called as VDB. Okay, we call it as voltage divider bias circuit. Why? Because this R1 and R2 are connected to the base, where this R1 and R2 will try to behave as voltage divider. Okay, this combination of R1 and R2, what you can see is considered to be a voltage divider. That is the reason it is called as voltage divider bias. Okay, now for this voltage bias circuit, let us write a series of equations so that we can try to generate the Q point. And that Q point is completely dependent on two values, which I told you already, IC and VC. Okay, so these two values is what the equation we need to generate for. Now, as we see, this is a voltage divider bias circuit. Like earlier we saw RB1 and RB2, which we discussed earlier in the previous biasing circuit. Here, VCC is connected to the top and R1 is connected here, and you see the base here, and you have R2 and you have a ground. Now, let me say this node is my VB, which is base voltage, right? As we did earlier, the base voltage VB will now be equal to, according to the voltage division rule, okay, voltage division rule, the total applied voltage from here to ground is VCC. Now, as you see in the circuit, the voltage across R2 is VB. The voltage across R2 is VB. So when I see the equation of VB, according to the voltage division rule, it will be equal to total voltage VCC multiplied by the resistance where the voltage is being calculated, which is R2, divided by R1 plus R2. R1 plus R2. Okay, so this is one way of finding, this is the way we find out VB value. Okay, now coming to your two resistors, these two resistors are meant to be in parallel. They both are considered to be in parallel. So R1 parallel with R2 is my base resistance, equivalent base resistance. Now if I want to draw an equivalent circuit of this, I can also draw in this way. So you have VCC connected to RB and given to base, and you have an RC connected to collector and given to VCC. You have an emitter connected to another resistor and connected to ground. So this circuit can be like this, and you see that this is your RB, which is, we know that it is equal to R1 parallel with R2. This is your RE and this is RC. Okay, so we can also write the equation in terms of it. The current flowing through this is my IB. The current flowing through this is IB, and this is IC, and this is your. Okay, now I got VB, I got RB through this particular circuit. Now my job is to know what is the equation for IC. Okay, to write the equation of IC, what I do is, okay, so let me mark here, it is VB. Okay, what we do is, we will try to write the equation for this particular loop. Okay, this particular loop. And I know that this is your base current IB. And here in terms of RE, if you take, this is IE. Okay, so therefore, if I try to write the equation for this, what I'll try to write here is, I can say the base voltage VB. Okay, so let me take this circuit which we have already written here. Okay, so I'll try to write in a proper sense. If I write the trivial equation for this particular loop, what will I get? So I can say it is VB. So the first voltage is VB minus IBRB. I can say it is minus IBRB minus. You have a base emitter voltage here. That is very important. You should always consider that. Base and emitter voltage, which is minus VBE minus. You also have a resistor RE here. So that is IE multiplied by RE. See, we are writing KVL, so all should be voltage terms. Equals 0. So it is VB minus IBRB minus VBE minus IER equals 0. Now I need to generate the equation for IE here so that we can easily say that your IE and IC are approximately equal. So once I will find out the equation for IE, I can easily say that it is equal to IC. So for that, what I need to do is, I do have an IE here. If I try to convert IB in terms of IE, then I can take IE common and somehow I can generate the equation. So we know that earlier, which we came across with this equation, my IE equals IC or IB plus IC. We knew this, right? And we also knew that IC equals beta times IB. In such case, my IE will be equal to IB plus beta times IB. So I can easily say that IE equals IB into beta plus 1. So in that case, I can further write this as IB equals IE by beta plus 1. Beta plus 1. So if I substitute this IB term into this equation, what will I get here is VB minus IE by beta plus 1 is your IB into RB minus VBE minus IERE equals 0. Now in this two term I can take IE common now. So what will I get? So I'll just write VB minus VBE, separate term. So which is, this is VB minus VBE. So I'll take minus IE common here. So I'll be getting what? RE plus RB by beta plus 1. RB by beta plus 1, which is equal to 0. Or I can easily say in this equation can be further written as VB minus VBE equals IE into RE plus RB by beta plus 1. Therefore, I can finally say that IE equals VB minus VBE whole thing divided by RE plus RB by beta plus 1. So this is your IE and this is also approximately equal to IC. Okay, so this is how the value IC can be obtained. Further, to find out what is VCE, further to write the equation for VCE, you need to go with the output loop. Which is the output loop? Now if you go with this loop, this complete loop, so this complete loop, I can write what is VCE. So for that, I'll try to write the separate circuit here. This one. So this is your RC. This is your RE. And let me say from year to year is your VCC. VCC. Now from year, which is your collector terminal, from year to year is your VC, and from year to year is VE. VE, and between this is your VCE. With this circuit, I can say that the voltage across collector emitter equals VC minus VE. Can I say that? Because see, from year to year it is VC, from year to year it is VE. If I want to know this gap, that will be equal to total value minus this remaining value. Right? Now, if I want to know what is VC, if I now want to know what is VC, my VC equals total voltage VCC minus ICRC. And we know that V equals IERE. So if I find out these two equations, if I find out these two values, I am easily able to find out what is the value of VCE. I am easily able to find out what is VCE. So with these two things, one thing I came to know what is IE, which is equal to IC. While another thing I came to know what is VCE. Therefore, these two equations will now give me the Q point value, VCE and IC. Once we found what is VCE and IC in this 4 resistor bias circuit, if we want to make the current IE or IC to be insensitive to temperature, or the beta should not vary in terms of temperature variations, we need to make sure that the VBE, what we have, the base emitter voltage, what we have, which we all know that which is equal to 0.7, and the equation what we wrote on the top for VB. Okay, so when we want to make the current IE to be independent of temperature increment, I need to make sure the first condition is the VB should be very high compared to VBE. Okay, so the base voltage should be very much greater compared to the base emitter voltage. It means that my value of VB should be very greater than the value 0.7. Okay, the value of VB should be very much high compared to 0.7, because we know VB is 0.7, which I told you already in the earlier video and also many discussions. The second condition, okay, the second condition for the IB to be independent of temperature increment, my resistor RE which I designed, okay, my resistor RE which I designed, or the value of RE that I'm going to connect to the emitter in 4 resistor bias circuit, that should be very great compared to RB by beta plus 1. Okay, that should be very much greater than the value RB by beta plus 1. So what happens here is, we know that earlier we derived the equation for IE, which was equal to, VB minus VBE. Okay, VB minus, which is base emitter voltage minus, base voltage minus base emitter voltage, divided by RE plus, RB divided by beta plus 1. This was the derivation which we did earlier. Now, if I use VB is very much greater than VBE, then the denominator, what you see here, the denominator and numerator term, what you see here in this equation, now this will become what? If VB is very greater than VB, this can be approximated to VB. And if this is very much, if RE is very high compared to RB by beta plus 1, I can approximate the denominator as RE. So therefore, finally, I can say that my IE, which is approximately equal to IC, we know that, can be, equated to VB divided by RE. So with this, you see that the emitter current is completely dependent on the external resistance RE and the voltage across the base that we measure. Okay, so this is how you can make IE to be insensitive to temperature in 4 resistor bias network. Okay, so I hope students, you have understood what is 4 resistor bias network. This is also considered to be a voltage divider biasing circuit. Okay, it's a very popular circuit. Normally, most of the oscillators and most of the voltage amplifiers that we design, we go with this voltage divider bias circuit. Okay, thank you.